How's that look on the board? Decent? Down a little bit? That's good. All right. Now, let's bridge a gap. Ryan, would you mind stopping that light on? That'd be awesome. We now have satisfied the requirements for the test. So now our pennies have satisfied the sample size, the consistency for trial, the binomial. We've got ourselves a center, p hat. So if you think back to yesterday, we had a three-tiered, get a single random sample, find the center, and find the margin of error. That's the whole point. Now over here, we know what our margin of error is already. We know that in the penny experiment, we know that p hat was 0.5, and the margin of error, we'll call it ME for margin of error, it's 0.06. The question is, where did that 0.06 come from? I'm going to give you an exceptionally good breakdown of that on the video that I record for you guys on Friday. And I'll try to get it done before Friday if I can and link it on. But here is the actual formula for margin of error for an estimated population proportion. For a margin of error, it's equal to a z-value times the square root of p hat, q hat, all divided by n. I've learned in the past not to drag you guys through a derivation of that in class. As a matter of fact, the only reason I want to talk about it a little bit right today is so you know where the 0.06 came from, the 6% came from. But I really want to break down what each of the pieces are. The video will explain to you why it's valid. And I encourage you, just be patient with me while I get that video uploaded for you and all your questions will be answered. I also have a derivation of it on the enrichment page of the website in Words, which you can check anytime you want to. But I'll get the video, I think the video will make it a little bit more approachable. Some of these pieces, you know what they are already. For example, p hat, you know what that is, don't you? Exactly, that's your 0.5. That's your sample proportion. What's your q hat going to be? Your q hat's going to be 0.5 as well. That is dry as a bone. Let's fix that. How are p hat and q hat related friends? Say that again. Good. Can I say complementary? Is that okay? That's Danielle. Good. Yeah, complement. I know what you mean when you say opposite. You mean when they sum to one. So whatever one is, the other one has. You guys are doing that over here. So call it complementary. I think that's the math term for it. Beautiful. You know what n is, don't you?
260?
Yep. And your sample size. That's your 260. Thank you, Kaylee. The last point that I want to hit before I send you guys out of here for your break is what this little z is. Because this is the guy that controls how wide your margin is. This right here, the p hat q hat over n square rooted, that's called one standard error. Do you remember that term from 243, standard error? Do you remember anything about it? And of course you can say no. Yeah, Eric's already saying no. It's totally fine. You can say no. What does standard error sound like from 243? Standard. Say it louder. It was beautiful. Deviation. Perfect. And standard error and standard deviation are essentially the same big idea. It represents the variation within a bunch of numbers. But the standard deviation is a purely descriptive statistic. In other words, you draw a bunch of numbers, you figure out what the average of those numbers is, and then you calculate the distance of each of the individual data points from the average, and you average that. That's essentially what a standard deviation is. And then you put your hands up and you say, I'm done. That's standard deviation. I can't go any further. What the standard error does, which is this chunk right here, that chunk right there allows you to make it inferential, which means it says, I drew this sample, I've got the standard deviation, but I want to adjust that standard deviation so that it stands for the entire population. That's why we call it standard error. That's why we call this block right here the root p hat q hat n. That's called the standard error.
I thought z was standard error.
You thought, say that again.
I thought Z was standard error.
Z is going to be the number of standard errors.
Got it.
Thank you, Kaylee. Thank you. You're 30 seconds ahead of me, my friend. It's beautiful. That's one standard error. Now, that might sound a little cryptic, maybe, but it's not. One standard error on a bell-shaped curve, which we just saw, which we'll always see based on these presumptions, contains how much of the data? One standard error. Or if you want to call it a standard deviation to think about it, call it that. But one of them contains how much of the data?
95.
Careful, that's 2.
67.
Nice. Good. About 2/3, 67, 68, somewhere in there, Will. That's one standard error or one standard deviation. One, but 2 of them contain 95%. 3 of them contain about almost 100% of them. Right? So what this is, and Kelly has put it out beautifully, that Z, the technical name for it is called a critical value. And I don't know your textbook well enough to know if they use that term or not. I'm not sure if they use that term or not. I haven't read that deeply into it yet. If they do, that's fine. What I think of it as, rather than a critical value, is it's a number of standard deviations from the average. Every one that you pick up a certain percentage. And you learned this back in 243. You learned this back in 243. So I think of it as a number of standard errors. So, if Z equals 1, which means it's just times 1, that means you're at 1 standard error, which means you have what percent of the data?
67?
Yep. 67 to 68%, somewhere in there. I always call that 2/3, but whatever it actually is. If you're at 2, you pick up roughly 95%. If you bump it out to 3, you essentially have it all, but it ends up being something like 99.7 or something along those lines. And you can go out as far or as near as you want. But after the break, I want to talk about why we usually use 2. 2 is the one that is used in industry as a standard, essentially. And I want to talk about why. And finally, let's see, I thought we were going before the break. We'll get it right after the break. Finally, understand where the 6% came from based off of that derivation. Cool? Well, take 5. You're definitely glazed. Yes. Go get unglazed, and we'll come back and chit-chat some more.